In this, we will get a little bit deeper into covalent bonding. We'll talk about polar covalent bonding. Polar means something that is positive and negative. To understand that, we will have to get into the concept of electronegativity. Then we'll go on to learning about formal charges, which are the charges on polyatomic ions. And in some cases, some neutral molecules also have formal charges. So we'll talk about that. You will learn about the concept of resonance. The first few slides are a little bit repetitive about bonding. So if you're not clear, then please make sure you listen to those slides again. One of the most important things that you will do from this chapter is to learn how to write Lewis structures. The Lewis structures for ionic compounds is not that hard. You just have the cation and the anion. The Lewis structures for covalent compound, as I said, are a little bit more complicated, okay? Because in case of covalent compounds, you can have the diatomic molecules like the H2Cl2, N2, O2. Those are easy to write, okay, not a problem. But then molecules can get very complicated also. You can have many atoms in there, and so you need to figure out how to write the Lewis structure for these kind of molecules. So this guideline hopefully will help you a little bit, and of course we will do all sorts of practice in class that should also help you out. So first of all, draw the skeleton structure of the molecule or ion. Okay, now we have to draw ions also. You remember all the polyatomic ions from chapter 2, phosphate, sulfate, carbonate, all of those. Those are all made of non-metals, okay, and they're sharing electrons. So we have to be able to write Lewis structure of those also. So anyway, draw the skeletal structure of the molecule by placing the lowest electronegative element in the center. The lowest electronegative element is of course coming from the periodic table. You can look at the periodic table for this. Is also the one that is on the left hand side. Okay, so remember, this is not for metals and non-metals. This is only for non-metals. Okay, that's where the sharing is going on. So don't go beyond group number 4. Okay, boron is the only element in group number 3 that is involved in covalent bonding. But other than that, group number 4 is where you start with covalent bonding. All right, so if we have something on the left hand side of the periodic table, that will go in the middle, and that is also the least electronegative element. One other hint over here for drawing the skeletal structure is try and keep it as compact as possible, okay, which means that if you have 5 atoms given to you, don't just draw them out in a line, okay, keep them as compact as possible, as symmetrical as possible, and that will make your life a lot easier, and it will make it easier for you to understand, okay, how to write the Lewis structure. So keep it compact, keep it symmetrical. The second thing you do then is add all the total number of valence electrons for each atom, not the central one, not just the outer ones, but everything. Okay, so add all the total valence electrons. Okay, and then what you're going to do is you can subtract electrons if it is a cation. So for example, in the ammonium ion, which is +1, you will subtract an electron, and if it is an anion, then you would add the electron, because an anion obviously has more electrons. So for example, for nitrate ion, you will add 1 more electron after the total valence electrons, and for sulfate, you will add the number of electrons for sulfur and 4 oxygens, and then you will add 2 more electrons because sulfate is -2. Then the third thing you do is start drawing the structure out, okay, which means that share 1 pair of electrons between each atom. No atom is going to be disconnected, okay, everything has to be connected. So there has to be at least 1 pair of electron, okay, that is being shared. You can have more, you can have double bond, triple bond, that's true, but you will have at least a single bond. And then what you will do is you will subtract those electrons from the total number of electrons from step number 2. So if you had 4 bonds, that means you have 8 electrons, so you will subtract 8 from the total number of electrons. Then what you will do is distribute the electrons that are left over, okay, to all the atoms such that all atoms are satisfied according to the octet rule. All right, so which means that no atom should have less or more electrons, okay. And in some cases, what's going to happen is that in case where you have charges, you're going to have to see which gets the positive, which gets the negative, which means which atom has some extra electrons, which has more electrons. And so or less electrons, and we will work on that in class also. Okay, and if there is no octet that is forming, then maybe you need to form multiple bonds. Okay, all of this sounds very complicated, but really it is not. It is quite simple. Once you start drawing out the Lewis structures, you will see it's a very systematic way of drawing Lewis structures. Okay, here are some hints from you for you, and the hints here will keep your life a little sane and make sure that you're on the right track when you write the Lewis structures. So for example, hydrogen and halogens, they will always have single bonds. Why? Because halogens need only one electron, and hydrogen also needs to share only one electron. The only time halogen will not have a single bond is when halogen is in the middle. Okay, and when is halogen in the middle? It is when it is a polyatomic ion, the chlorates and the hypochlorates and all that. Okay, so other than that, if there is halogen in there, then it will be a terminal atom, which means a single bond. Oxygen and sulfur will always have two bonds. Okay, now I'm giving you all these hints, but then I'm also telling you exceptions. Okay, because in all these cases you will always have exceptions, and you have to be ready for those exceptions. Okay, so for example, halogens can be in the middle, okay, and they can have more than one bond. Similarly here for oxygen sulfur, oxygen will be in the middle, it can have two bonds, but sulfur can have more than two bonds in some cases. Okay, so you have to watch out for that. But in any case, in most cases, oxygen and sulfur will have two bonds. The two bonds can be two single bonds, or it can be one double bond. Nitrogen, phosphorus, 3 bonds. Carbon, 4 bonds. Okay, and so this is how it goes. Carbon, 4 bonds. This is never, ever going to change. Okay, nitrogen, 3 bonds is never going to change. All right, so long it's a neutral molecule, these things will not change. Sulfur, phosphorus, halogens, sometimes things change in there. Okay, and we'll deal with that as we get to it. So here are the steps, and you may want to keep the slide, okay, a little bit. This explains to you what we just talked about. Okay, so let's start with CH4 here. This is methane, and the first step was to draw a skeletal structure. Okay, this is the skeletal structure for CH4, keeping carbon in the middle because carbon is the least electronegative element and hydrogen is not. Again, you cannot draw everything in a line. Okay, so as I said to you, keep it symmetrical and keep it compact. All right, so this is a nice compact symmetrical structure with carbon in the middle and 4 hydrogens on the side. Then the total number of valence electrons are 8. How? 4 coming from carbon and 4 coming from hydrogen. Okay, so that's the total number of electrons. Step number 3, are there electrons left over? So what you look at now is the total number of electrons you counted, which is 8. And then you look at the bonds that you formed over here, which is 1, 2, 3, 4. Each bond has a pair of electrons, and so that is 8 electrons. So 8 minus 8, 0, which means that there are no electrons left over. So therefore, this is the structure of CH4. Okay, there's nothing else to do. CCl4. Now CH4, CCl4 are kind of similar, okay, because you have the 4 atoms here also with carbon and 4 atoms were here also with carbon. If they were just hydrogen here, now you have chlorine. So again, start with the compact structure. Okay, chlorine is more electronegative than carbon, so carbon goes in the middle. Now the total number of valence electrons are a lot more. Why? Because chlorine has 7 electrons and carbon has 4. So 7 times 4, that's 28, plus 4, that's 32. Okay, so that's the total number of valence electrons. And then you go ahead and subtract what you have formed the bonds of. So you form 4 bonds, 1, 2, 3, 4. So you take the total number of electrons, 32, and subtract 8 from it, and you have 24 electrons left over. Now, where do you place those 24 electrons? If you look at carbon, carbon is already happy. Okay, it's got 8 electrons and it does not need any more electrons. So which means that you can take those 4 electrons and you can distribute them all over the chlorine. So 24 divided by 4 is 6, and so you give 6 electrons each to chlorine. Okay, this is how it works. So similarly, go on for these two yourself, and I'll cover Cn minus, which is a cyanide ion, because this is a negative ion. So here we have only 2 atoms, so C and N joined together 1. Now, where is this 10 coming from? Total number of valence electrons. Carbon has 4 and nitrogen has 5. So that's 4 plus 5, 9 but we have one negative charge, so therefore you have to add that on here, so which gives you 10. Okay, so 4 plus 5 plus 1, that gives you a total of 10 electrons. How many are involved in bond? 2 right now. So 10 minus 2 is 8 electrons. So which means that we have 8 electrons left over to account for. So then we go ahead and distribute the electrons as well as we can. Carbon can have only 4 electrons, okay? Maximum it can have 8 electrons when it's fully bonded. So this is what the structure would look like if you distribute 2 electrons on carbon and then 6 on nitrogen. So nitrogen is pretty happy right now, but carbon is not happy. Nitrogen is okay because it's got the 8 electrons, 6 from here and 2 from the bond. So it's sharing 8 electrons and it's fine. But carbon is not happy because it's got only 4 electrons, and technically speaking it should have 8 electrons. That's the whole reason for it to bond. So it's not very happy. So what we have to do then to make it happy is make sure that we share more electrons between carbon and nitrogen. Okay, so carbon can have up to 3 or 4 bonds. So here we form 3 bonds more, excuse me, 2 more bonds between carbon and nitrogen. So now carbon is happy because it's got 2 electrons over here and it's got 1, 2, 3, so 6 electrons over here. So now we have 8 electrons. Okay, 1, 2, 3, 4, and fourth one is over here. So 3 pairs here, 1 pair here. Nitrogen is pretty happy also. Okay, so you can see that this structure where carbon and nitrogen are sharing more electrons is a lot more stable structure than what we had before with just one pair of electron being shared. So now you go ahead and put square brackets all around and put the negative outside because that extra electron is really helping out over here. Okay, and because this is a polyatomic ion, you have to draw the square brackets. Okay, in case of oxygen over here or water here, all the other ones you did not have to draw the square bracket, but because you have an extra electron, where do you put that? Do you put that on carbon? Do you put that on nitrogen? You don't know that yet. Okay, and so therefore you go ahead and put the square bracket and put the negative outside. So let's go over polar covalent bond now. This is, of course, a covalent bond, which means there is sharing going on. In ionic bond, it's a little bit different because it's inherently polar because there is a positive and negative. But in a polar covalent bond, you have slight charge distribution. So in any case, there are two kinds of covalent bond. One is the non-polar covalent bond in which the electrons are shared equally by all the atoms in there. And then there is the polar covalent bond in which the electrons are shared unequally, which means one atom is actually pulling electrons towards itself or just a little greedy, wants a little bit more. Okay, and so that is called a polar covalent. Remember, polar means something like positive, negative, north or south. For us in covalent bond, it's going to be more about positive and negative. So here, looking at this little table, it shows a little bit using the charges how to look at this. So here is the pure covalent bond in which there is a complete sharing of electrons, equal sharing of electrons. And then here is the polar covalent bond in which you can see some partial charges here. That little symbol there, that is actually delta, delta plus, delta negative. And the delta just means a small amount. Okay, that's all it is. It's not a large, it's a small amount. So in case of a polar covalent bond, you have a delta positive and a delta negative charge. The X here shows that it's negative, which means that's the one that's actually pulling the electrons towards itself. So M is a little bit electron poor and X is a little bit electron rich, okay, in this case. So not the same as a pure covalent bond. And then we have the ionic bond. In ionic bond, it's a complete transfer of electrons. So of course, one element, X over here, has more electrons than M, okay, which has given away its electrons. So this is a complete polar molecule or compound, whereas in a polar covalent, there is just a slight charge, okay, that you have. You can see this as far as an electron density is concerned, and these are the different colors that you would get. Red is considered to be a high electron density, which means more negative. green is intermediate, and blue is generally considered to be the low electron density or more of a positive. Okay, so in case of hydrogen, which is a pure covalent bond, okay, which means everything is being shared equally, the electrons are in the middle, and there is a nice distinct line here. You can see there is, no distortion going on. In case of HF, which is hydrogen fluoride, now you actually have a little bit distribution here. You can see that the electrons are more towards fluorine, and then the hydrogen over here is slightly more positive. Okay, it's blue in color. And then sodium fluoride, of course, here you have the fluorine, which is completely negative, red, and then sodium, which is blue. Okay, so you can look at these electronic density charts as well. Of course, we're not going to be looking so much at these. We will be looking at the elements and be able to predict from there as to which one has a polar covalent bond and which one is a pure covalent bond. And the answer is electronegativity. Okay, and electronegativity is a measure of the ability of an atom to attract bonding electrons to itself. So electronegativity is a property of an element. There is nothing you can do about this. This is how it is. Okay, so for example, like the boiling point of water is 100 degrees centigrade. That is what it is. Okay, so all you can do now is deal with it. Okay, so similarly here also electronegativity is what it is. All we can do now is learn about it and apply it. Okay, so electronegativity is the measure of the ability of an atom to attract bonding electrons towards itself. The nice thing is there is a trend. Okay, and so the trend is that electronegativity increases as you go towards the right hand side, and as you go down, the electronegativity decreases. So these are the two trends. Okay, increases to the right, decreases to the bottom. Okay, as you go down the periodic table. So given all of this, fluorine becomes the most electronegative element. If you can note over here, the noble gases are not here, and noble gases are not here because they don't even bond. Okay, and so we finish here at the halogens. So fluorine has the highest electronegativity, followed by oxygen and then nitrogen. Nitrogen and chlorine are quite similar. Okay, but you will see that nitrogen, oxygen, and fluorine, they give so many different properties to molecules because of this property, okay, because of this electronegativity and their pull of electrons. So look at the metals over here. They don't attract electrons at all. Okay, so they're very nice cool blue because they don't attract electrons. So electronegativity increases only towards the right, which means it's a property of the non-metals. Again, if you keep going down in a group, for example, from fluorine to iodine, you can see that the numbers are decreasing. So by the time you come to iodine, really there is not much electronegativity going on, okay, over here. So most of the time iodine compounds will be pretty much non-polar, okay, and whereas fluorine, oxygen, nitrogen, chlorine, all of these elements will cause some sort of polarity in the bond because they will cause this unequal distribution of electrons. So how do you know whether something is a polar bond or not? Well, first of all, you just look at that in the periodic table, okay? And again, those numbers are not given to you, so you just have to know the trend, okay, that's going on. And then the second part is that when you're working on your own, okay, then you can use that periodic table and look at the numbers and subtract the two electronegativity numbers, okay? And if the electronegativity numbers after subtraction gives you 0.5 or less, it means that the bond is non-polar. Okay, if it is more, then the bond is definitely polar. And again, you can do that only when you have the numbers with you, which you will not have in an exam. So it's much easier to remember these trends. Okay. The other thing is to go ahead and try and subtract a few of these elements. Okay, so for example, subtract the carbon from hydrogen, subtract carbon and iodine numbers and see what you get, and hopefully you'll remember that trend when you get to the exam. Okay, and so if the number is 0.5 or less, then the bond is non-polar. If it is a large number, then the bond is definitely polar. Okay, so if these are the three bonds you were looking at, then you will just go ahead and subtract the numbers. But then, as I said, you will not have that in the exam, so you have to remember that Na and F, so sodium and fluorine, metal, non-metal. Okay, so definitely between metal and non-metal, you have to have a polar bond. Between oxygen and hydrogen, you have to have a polar bond. Why? Because oxygen is very high in electronegativity. And then carbon and nitrogen will have the less polar bond, or the least polar bond here, because nitrogen is after oxygen on the periodic table for electronegativity. Okay, and so therefore the CN bond is not so much polar. But that's how you would do this. Okay, so again, no numbers, okay, in the exam. You have to know the trend. So here is an example for writing another Lewis structure, and this one is for nitrate. And I took a polyatomic over here, so you have a little bit more of an idea how to draw when you have multiple atoms, okay, in there. So first of all, we'll draw the skeletal structure as we did before, okay, and the least electronegative element is nitrogen, between nitrogen and oxygen, so we put that in the center, okay, and then connect each of the oxygen with one single bond. Then you go ahead and add the valence electrons, okay, and remember to add 1 for the charge, okay, on the nitrate ion. So 1 times 5, okay, which is nitrogen, and then of course oxygen has 6 electrons plus 1. So we have a total of 24 valence electrons. Then the next thing we do is we subtract 2 electrons for each of the bond that we have already formed. Okay, that was the skeletal structure that we started with, and so you subtract the 6 electrons, okay, that we have. So which means we have 18 electrons left, and now what we will do is go ahead and place those 18 electrons and try to complete the entire octet, okay, over here. So now oxygen is happy, oxygen is happy, oxygen is happy. Why? Because it has, each of them has 8 electrons, 1, 2, 3, 4 pairs of electron. But nitrogen is not very happy. Nitrogen has got 6 electrons here, so that's not very happy. So what we're going to do then is we're going to rewrite the structure a little bit. Okay, and so we'll place some extra electrons in the central atom, okay, and we'll draw a multiple bond, all right, between nitrogen and oxygen. So now 1, 2, 3, 4, oxygen happy, 1, 2, 3, 4, this oxygen is happy, nitrogen 1, 2, 3, 4, this nitrogen is happy, and 1, 2, 3, 4, this oxygen also has a stable octet. Okay, and so we are accounted for all the 24 electrons, and then again we draw the square bracket and the negative charge, okay, on here. How do you know when to draw the multiple bonds? Okay, first of all, you have to see if the element is even capable of forming a multiple bond. So for example, if there was chlorine or hydrogen, you would not do that. Okay, but because there is oxygen, carbon, or nitrogen, then you can have multiple bonds. Okay, and remember the goal always is to get the stable octet. Okay, that's the goal. It's not about single bonds and double bonds. It's about stable octet. Now for formal charges. Okay, so what we were talking about before, as in the cyanide ion, as to where to put the negative charge. Okay, where do you put that? So in order to calculate, okay, and see where that extra charge goes, this is the formula that you will use for calculating that. So what you do is you take the total number of valence electrons, you take the total number of non-bonding electrons, those are the ones that were outside, remember the lone pair of electrons, and you also subtract the bonding electrons and half of those, okay, for each element. Okay, that's what you have to do in order to figure out the formal charge. So again, for formal charge of an element, take the total valence electrons of that element. Take the total number of non-bonding electrons of that element, so subtract those two, and then subtract half of the bonding electrons, because remember half of them are coming from the other element, all right, so you can't use those. So for example, let's take for water, okay, and here is water, and H2O, oxygen in the middle, oxygen with 1, 2, 3, 4, 5, 6 electrons, and hydrogen is bringing in 1 electron, okay, from its part. So then to calculate for hydrogen, the original number of valence electrons, so the valence electrons on hydrogen are 1. The total number of bonding electrons on hydrogen is 0, okay, because there is no electron left over. So total number of non-bonding electrons are 0. So subtract that. And then half of the bonding electrons, okay, so which means that since it was sharing only one pair of electrons, take half of that. So subtract that and you get a formal charge of 0, okay, which means hydrogen has no charge left over, which is good, okay, because this is a neutral molecule, okay. So technically speaking, there shouldn't be any charge, but this is a method and a process to do this, because in some cases there are some charges but the molecule is still neutral. Okay, then let's work on oxygen. In case of oxygen, the original number of valence electrons is 6. Okay, that's what we start with. The number of non-bonding electrons are 4. So one pair here and one pair here. These were the non-bonding electrons. So subtract those 4 electrons from there, and then half of the bonding electrons. Because it has 2 bonds over here, then it means you are sharing 2 electrons, and so subtract those 2 electrons. And so 6 minus 4 minus 2 gives you 0. So which means oxygen also has a formal charge of 0. If you don't want to do the half of the total bonding of electrons, that's fine. You don't have to do that. Just count the number of bonds. That's what I do when I'm calculating the formal charge. I don't do the half thing. I just say that oxygen has 2 bonds and therefore I'm going to subtract 2, okay, from here, because that's what it will come out to be. The formal charges are not real charges. Okay, the real charges will be the nitrate, for example, sulfate, those ones. Formal charges are just within the molecule itself. Okay, as I said, in some cases you have formal charges, but the molecule will still be neutral. Okay, so these are not really real. So then the question that you're probably thinking about is, what is the importance of formal charge? Okay, and formal charges are important to determine the right kind of structure. All right, so there are a few rules that we need to follow for formal structures. Is that a Lewis structure that has no formal charge is generally better than the one that has a formal charge. So which means if you have a positive or a negative, that is not as stable as a neutral substance or a neutral molecule. If you have to have a charge, then a small formal charge is good. Okay, so for example, just a -1 or just a -2 is good. Okay, you cannot have +1 and -1 on the same one. Those are not stable. In some cases they are, but generally if you can avoid having charges, it's better. And then the last rule here is that the negative charge that you should have should be more on the more electronegative element. So whatever is on the right hand side of the periodic table will get the charge. Okay, will get the negative charge. Whatever is on the left hand side of the periodic table will get the positive charge. Okay, that's what the rule is. So let's take an example, okay, of H2CO, and you're trying to draw the Lewis structure of this one. Okay, and you're thinking, okay, how am I going to do this? I have 2 hydrogen atoms and I have a carbon and I have an oxygen. Okay, how am I going to put this together? So you come up with 2 different skeletal structures. Okay, one in which case you just took everything in a line, and of course you are smart, so you go ahead and put hydrogens at the end, because you know that hydrogens are always terminal atoms because they can form only one bond. Okay, and so you have one of these skeletal structures, and the other skeletal structure is like this, where you put carbon in the middle and only 3 atoms on the side. Okay, here carbon is in the middle, but you have only 2 atoms on the side. Oxygen here also is going to be bonding with 2 elements over here. Okay, so then we'll go ahead and put all the bonds together, okay, over here. So this is what the bonding should look like in case of the first one, okay, where you have carbon. So oxygen, remember, can have up to 2 bonds, okay. Carbon can have up to 4 bonds, but here you're drawing only 3 bonds, and hydrogen has 1 bond, hydrogen has 1 bond, so that is all fine. And then of course you learned that oxygen can have 2 bonds, so 3 bonds, not very good, but 1, 2, 3, 4, that is still the stable octet. 1, 2, 3, 4, that is still the stable octet. Okay, so the most important thing here that you followed is that there should be a stable octet, okay, for each of the elements. Let's look at over here for this structure, and in this case you have carbon 1, 2, 3, 4. So here you have 4 pairs of electrons, so 8 electrons. Yes, carbon is very happy. Oxygen has 1, 2, 3, 4. So yes, carbon is also happy. Okay, so which structure is the better one? That comes from this answer right here with the positive and negative. Okay, and the fact that when you start calculating the formal charges for carbon, it will be 4 minus 2 minus 3. Okay, 4 coming from the 4 valence electrons, 2 coming from the fact that you have 2 electrons left over on carbon, and 3 coming from the fact that you have 3 bonds on carbon. So carbon has a negative 1 charge. You do the same calculation for oxygen, and oxygen has 6 valence electrons, 2 electrons that are left over that are not bonded, and then 3 electrons that are actually bonded. So 1, 2, 3 electrons, and then by the time you calculate the charge here, this is plus 1. Okay, so which means carbon here has a formal charge of -1, and oxygen here is +1. Now remember, whether this is -1 and +1, it doesn't matter, because in totality the molecule is still neutral, because there is a positive and then there is a negative. Okay, so this is still a neutral molecule. The question is which structure is more stable, this one or this one. Okay, so now we'll calculate the formal charges for carbon and oxygen over here. So carbon here, 4 valence electrons, no electrons left over, and then 4 that are bonded here, so that gives a total charge of 0. And then oxygen, 6 valence electrons, 1, 2, 3, 4, 4 electrons that are left over, and then 2 that are bonded. So 6 minus 4 minus 2 gives 0. So in this structure, both carbon and oxygen have 0 formal charge, and therefore this structure is going to be the more stable structure. Okay, so that's what we use the formal charge for, to determine what is the right structure of any compound. Now let's look at a concept called resonance. Resonance is defined as the movement of electrons over 2 bonds, and sometimes it can be over more bonds also. And what happens in these cases is that you can actually write more than one structure for the molecule or the ion, and then all those structures are valid. Okay, so for example, if we take the nitrite ion, which is NO2-, okay, and write the Lewis structure of this, this is what it would look like. Okay, it turns out that these 2 bonds, okay, in between nitrogen and oxygen, and then the nitrogen and oxygen here, one is a single bond, the other one is a double bond, but it turns out that these 2 bonds are completely identical, okay, in their structure. So how is that possible? Okay, that they are actually the same, where one is single but the other one is a double bond. So it should not be identical, technically speaking, but they are. So the way to explain them is by showing that electrons can actually move around. So what happens then is that the extra pair of electrons here, remember in a double bond you have 2 pairs of electrons. So one of the pair of electrons from between nitrogen and oxygen will move to the other bond. Okay, now this movement is only over to the next atom. Okay, it doesn't happen over 3 atoms or so. It's just to the next one. So the electrons will move from here to here, and so now you have the double bond on the left side, whereas you had it on the right side before. And this kind of a movement is a very rapid movement. It happens very fast, and it happens so fast that neither you have a single bond nor a double bond then in the nitrite ion. Both of these bonds are going to be equal, and that's what we saw before, is that these are identical. And this is something that you find out from studying the molecule. This is not something that you can know, but of course once you learn about resonance, then you can predict if a molecule is going to have resonance or not. Okay, but now that you know about it, you should be able to predict. But in any case, what happens here then is that there is no double bond, there is no single bond, there is what we call a hybrid. Okay, and the hybrid is what describes the nitrite ion. In this case then, these two bonds are not single or double. It's something in between the single and a double bond. Why? Because electrons are moving so fast, okay, between the left and the right. And then, of course, we have this wonderful arrow that you see in the middle. This is what we call the double-headed arrow, and that is for resonance. Okay, this is the third kind of arrow you are learning in Gen Chem. One of them is a simple one that you write in reactions, which is yield. The second one you just learned a few minutes ago regarding polar bonds, where you showed the direction of the negative charge. And now here's the third one, where you have a double-headed arrow, and this indicates resonance. Your takeaways from this chapter or this presentation is, of course, the Lewis structures. There's nothing you can do without Lewis structures, so I covered it again here for you. The bond polarity, and the only way you can understand bond polarity is by knowing electronegativity. So again, know the trend on the periodic table as to what it is like, and then, of course, you should know how to calculate the formal charges of each of the elements that we have in any compound. Regarding the resonance structures, I know it's a new concept and it's sometimes a little bit tough, but please know that you should know the concept of resonance. So if I give you two structures, you should be able to tell me the difference between the two, or at least tell me if they are resonance or not.